No human being alive today will ever leave the solar system. Almost certainly, no human being ever will. That is not despair, and it is not a failure of nerve or money. It is a plain fact of physics, and the reason for it is stranger than you would guess. You might assume the thing holding us in is the sun's gravity, but we beat the sun's gravity almost 50 years ago, with a probe built in the 1970s that is drifting out of its reach forever. The fastest machine we have ever built moves at more than 600,000 kilometers an hour, and even it would need 2,500 years just to reach the edge of our own solar system, where there is nothing at all. And the moment you go fast enough to beat that emptiness, the emptiness turns into a wall of fire, where a single grain of dust hits with the force of a bomb. There is a reason all of this closes into a cage that no living thing can pass. And by the end of tonight, you will know exactly what it is. Get cozy. Subscribe if you haven't yet, because by the end of this, the open sky above you will feel less like a door and more like the shape of home. Now, let's slowly ease into this. Part 1. The direction with no flaw. Point straight up. Right now, wherever you are, lift a hand and aim a finger at the ceiling, and then imagine the ceiling gone, and the roof above it gone, and the sky above that gone as well. You are pointing in a real direction. It has a name in physics. It is the direction that leads out of the thin shell of air we live in, past the last wisp of atmosphere, and into the open space between the worlds. And here is the first strange thing about that direction, the thing worth sitting with before anything else tonight. There is nothing holding you down. There is no lid over your head, no dome, no wall you would have to punch through to leave. The way out is completely, permanently open, and yet no human being alive today will ever travel it to its end. Almost certainly, no human being ever will. That sentence deserves to be said slowly, because it sounds like the kind of thing people say for effect, and it is not. It is a plain description of where the physics stands. Everyone reading the future of our species has assumed, quietly, that leaving is only a matter of time. We have told ourselves the story so often that it feels less like a hope and more like a schedule. First the moon, then Mars, then the outer planets, then the nearer stars, then the galaxy, each step following the last, the way a child grows into an adult. It feels inevitable. It feels like the natural shape of what a curious species does once it gets clever enough. And the trouble is that the universe was not consulted on this schedule, and the universe has arranged things so that the schedule quietly stops. So what is stopping us? That is the whole question of tonight, and I want to be careful with it, because the obvious answer is wrong, and the wrongness of the obvious answer is where the real story begins. The obvious answer is gravity. You feel it pinning you to your chair. You watch rockets strain and roar and burn thousands of tons of fuel just to lift a small capsule off the ground. It is natural to assume that the thing holding us on Earth is the same thing holding us in the solar system, that the sun has us on some enormous invisible leash, and that escaping means somehow snapping it. That picture is intuitive, and it is almost entirely mistaken. We already snapped the leash. In 1977, we launched 2 small probes, and one of them, still flying, has long since exceeded the speed it needs to break free of the sun's gravity forever. It is not on a loop. It is not going to fall back. It is on an open path that leads out and never returns. And on a long enough timescale, it will drift among other stars. Whatever is trapping us then, it is not the sun's grip, because a machine built with 1970s electronics beat that grip almost 50 years ago. The barrier is something else. It is something stranger, and it does not pull. It does not grab you and hold on. It just sits there, made of distance and emptiness, and a few unbending rules, and it turns out to be far harder to beat than any force ever could be. This is the part that unsettles me the most, and it is why I wanted to open here rather than with rockets and numbers. A wall you can understand. A wall has a location. You can walk up to it, put your hand on it, look for a door, dig underneath, climb over. A force you can understand too, because a force is a thing you push against, and pushing is what engineering is for. But the barrier around the solar system has no location, and it is not a force. There is no ceiling to break through. There is no single point in space where you cross from trapped to free. You could fly outward for 1,000 years in a straight line and never once feel the barrier, never see it, never hit it, and still never get anywhere. Because the barrier is not in front of you. The barrier is the shape of the whole situation. It is woven into how big space is, into how fast anything is allowed to move, into how much energy it costs to move that fast, and into what the empty dark does to you when you finally try. 4 things, and not one of them is a wall you could point at. I called this a strange reason in the title, and I meant it precisely. It would be one thing if there were a single obstacle, a boss at the gate, a problem we could name, and then throw a century of engineering at. There is not. There is instead a quiet conspiracy of separate physical laws, each of which, taken by itself, would let us through. Any one of them alone, we could probably beat. It is only when you line them all up that they close, like the tumblers of a lock that has no key, and the space between our star and the next becomes something no carbon-based creature can cross in a way that would ever matter. By the end of tonight, you will know exactly what those 4 things are, how each one works, and why together they form a cage that fits every living thing in the universe, and not just us. It helps to say plainly what escape even means here, because the word does a lot of quiet work. We are not asking whether a piece of metal can leave. That is settled. Voyager will leave. A golf ball flung hard enough would leave. The question is whether a living thing, a crew of warm bodies that need food and water and shielding and each other, can cross from our star to another star in a span of time, and at a cost that would ever be worth doing, and arrive as something other than a tomb. That is the escape that matters, the only one that would change what our species is, and it is that escape, the meaningful one, that the 4 walls close around. A probe escaping the sun's gravity is like a message in a bottle slipping out to sea. It is not the same as a person sailing to a new continent and building a life there. One we have done. The other is the thing the universe seems to have quietly forbidden. And I will make you one promise about the ending, because I think it changes how the whole story feels. This is not, in the end, a sad video. The most surprising thing I found in all of this is not that the barrier exists. It is what the barrier is made of. Because when you finally see all 4 walls clearly, and you ask where they come from, you discover that they are the same rules, the exact same handful of laws that allowed a warm, wet, thinking thing to exist on a small planet and look up and wonder about the stars in the first place. The cage and the cradle turn out to be one object, seen from 2 sides. But we are a long way from that yet. First, we have to feel how large this really is, and to feel it, we have to start where all travel starts. We have to start with speed. Part 2. The velocity ladder. Speed is the thing that eats distance. If a place is far away, the answer, in every part of ordinary life, is to go faster, and the distance shrinks in proportion. Walk, and a journey takes a day. Drive, and it takes an hour. Fly, and it takes minutes. Our whole intuition about far and near was built by this simple trade, and it works beautifully at every scale we evolved to handle. So the honest way to feel the size of space is to climb the ladder of our fastest speeds, rung by rung, and watch what happens to the distances as we do, because the trade that always worked is about to break in front of us, and it is important to watch it break slowly. Start with a passenger jet, the fastest most people will ever personally travel, cruising at about 900 kilometers per hour. At that speed, you cross an ocean in a night. Now step up to the fastest speed any human body has ever moved. That record does not belong to a fighter pilot or a race car driver. It belongs to the astronauts of Apollo 10, who in May of 1969, falling back toward Earth from the Moon, reached very nearly 40,000 kilometers per hour. That is about 44 times faster than the jet. It is a speed that would carry you from one side of the planet to the other in under an hour, and for more than half a century, no human being has gone faster. Hold that number for a moment, because it is the ceiling of human experience. 40,000 kilometers per hour is as fast as a person has ever been. But machines can go faster than people, and the fastest machine we have ever built is a genuinely astonishing thing. It is called the Parker Solar Probe, and it is doing something clever to reach its speed, something worth understanding, because it is the closest thing physics offers to a cheat. The probe is not simply burning fuel to accelerate, it is diving, over and over, past the planet Venus, and each time it passes, it steals a little of Venus's orbital motion, swinging around the planet's gravity, like a stone in a sling, and coming away faster than it went in. It has done this again and again over several years, tightening its loops, falling closer and closer to the Sun, and near its closest approaches, it moves at something on the order of 635,000 kilometers per hour. At its very fastest, at the bottom of its closest dive toward the Sun, it has pushed beyond 680,000. Let that number settle, because it is hard to hold. 600,000 kilometers an hour and more. That is fast enough to circle the entire Earth in about 4 minutes. It is fast enough to cover the distance from here to the Moon, the 3-day voyage that Apollo made, in roughly half an hour. It is about 16 times faster than the fastest human has ever traveled, and something like 700 times faster than that jet crossing the ocean. There is nothing humanity has ever made that moves faster than this small, brave machine falling toward our star. If speed is the thing that eats distance, then the Parker Solar Probe is the sharpest tooth we have ever forged. Every record on this ladder took an extraordinary effort to set, and each one stood for years or decades before the next arrived. This is the frontier of what is physically possible for us, right now, the accumulated result of every trick and every dollar and every clever engineer we could bring to the problem of moving fast. It is the best we have. It is worth remembering that as we go on, because the best we have is about to be measured against the real thing, and the measurement is not kind. It is worth pausing on why the gravity assist trick works at all, because it tells you something about how thin the margins are out here. When the probe swings past Venus, it does not touch the planet or draw fuel from it in any ordinary sense. It simply falls toward Venus, whips around, and falls away again. And because Venus itself is moving around the Sun at enormous speed, the probe can come away carrying some of that borrowed motion. It is a way of stealing speed from a planet's orbit without the planet noticing the loss, because the planet is so unimaginably more massive than the probe. And the reason we go to all this trouble, the reason we do not simply build a bigger engine and burn our way to that speed directly, is the very thing this whole video is circling toward. Reaching high speed by brute force is so expensive that even our best rockets cannot do it, and so we resort to elaborate slingshots around planets, spending years of careful diving just to reach a speed that, as you are about to see, is still hopelessly, laughably slow against the distances that matter. And notice what the probe is doing with all that hard-won speed. It is not heading out toward the stars. It is falling inward, toward the Sun, into the one direction, where a small nudge of the engines and the Sun's own pull do most of the work for you. Going down a gravity well is easy. The Sun helps. Going up and out, away from the Sun, against its pull, and across the enormous flat emptiness beyond, gets no such help, and that is the direction we actually need. So even the fastest object we have ever built earned its speed by going the wrong way, downhill, with gravity as an ally, in the one corner of the solar system where speed is cheap. Turn that same machine around and aim it outward, into the dark, and everything gets harder. So let us do something generous and a little bit playful with it. Let us pretend, just for the length of this journey, that we could take that speed and give it to a crewed ship, not a probe the size of a car, but a real vessel with people aboard, provisioned and shielded, able to hold 635,000 kilometers per hour, steadily, hour after hour, year after year, pointed straight out of the solar system. This is already a fantasy, because nothing we can build could actually do this with a crew, but let us grant it anyway, because I want the distances to be the villain of this first act and not the engineering. Give us the fastest speed our species has ever achieved, make it endless, and let us see how far it gets us. Let us find out whether our sharpest tooth is sharp enough to bite through the dark. The first stops are wonderful. They are, in fact, better than anything our real rockets can offer, and for a while, the fantasy feels like a triumph. And that is exactly the trap, because the ladder of speed we just climbed felt like progress, each rung a comfortable multiple of the last, and it has quietly convinced us that we are fast. We are not fast. We are about to find out that the words we have been using, words like far and fast and soon, were calibrated for hills and oceans, and that they mean almost nothing out here. The velocity ladder gave us pride. The next thing it gives us is the exact measure of how little that pride is worth, because now we take our impossibly fast ship and we start counting the distances it actually has to cross, and we begin, for the first time, to zoom out. Part 3. The zoom out that empties the room. You are aboard the fast ship now. Come with me and ride it, because the numbers only mean something if you feel them arrive one at a time. The engines are silent, holding 635,000 kilometers per hour, and the first thing you pass is Mars. On today's real rockets, Mars is a 7 to 10 month voyage, a distance that has defined the outer limit of every serious human plan for the next century. On our ship, Mars is 2 weeks away. 2 weeks. A rust-colored disk grows in the window, hangs there, and slips behind you, and it is not even a proper waypoint, just a thing you pass. This is going well. This is the fantasy paying off. Keep going. Jupiter, then the cold outer worlds, and then Pluto, that tiny distant point that took a real probe nearly a decade to reach. On our ship, Pluto arrives after about a year. A year is a long time to be in a metal room, but it is a human span, the length of a deployment, a school year, a season of your life, and at the end of it, you have crossed to the edge of the classical solar system. Still going well, mostly. Push on, and you reach the heliopause, the place where the wind streaming off the sun finally loses its fight against the space between the stars, a kind of invisible shoreline. And a little past that, after 50 years of its own flight, you catch and pass Voyager, the machine that broke the sun's leash, the most distant thing our species has ever sent. You pass 50 years of travel in a single afternoon. It should feel like a victory. But the counter keeps climbing, and the view stops changing, and this is where the feeling turns. A year becomes 10 years. 10 becomes 100. The windows show the same unbroken black they showed on the first day. There are no waypoints now. There is no rust-colored disk, no pale coin of a distant world, nothing to slip behind you and mark that you have moved. 100 years becomes 500. 500 becomes 1,000. You have now been flying at the fastest speed our species has ever achieved for the entire span from the fall of the Roman Empire to today. And the black in the window is identical to the black you started with. And the true edge of the solar system, the outer boundary of the Oort cloud, that vast spherical shell of dormant comets that marks where the sun's territory really ends, is still not here. You reach it, finally, after about 2,500 years. Sit in that number, because it is the first wall showing its face. 2,500 years is the span from the founding of the Roman Republic to the present day, passed entirely inside a metal room, at a speed no crewed vessel could ever really hold, just to reach the edge of our own solar system. And when you arrive, there is nothing there. This is the part that hollows out the chest. It is not that the journey is dangerous. It is that the journey is empty. You have crossed 25 centuries of the fastest travel imaginable, and the reward is a region so sparse, so close to a perfect vacuum, that you would sail through the Oort cloud for years without ever seeing one of its comets. The barrier, the very first face of it, is made of nothing. It is a barrier of pure distance and pure emptiness, and it is the strangest kind of wall, because there is nothing to push against. And here is the cruelty that space keeps playing on us, the pattern you should learn to brace for tonight, because it repeats. There is always a place that seems impossibly far, and then, with human ingenuity and enough money and enough patience, we find we can imagine reaching it. And just as hope returns, you zoom out one more time, and all of it drains away again, because the place you fought to reach turns out to be the near edge of something 1,000 times larger. We felt it just now. Pluto seemed like the end, and it was not even close. The heliopause seemed like the edge, and the Oort cloud is 1,000 times farther still. Every time we think we have found the far shore, the camera pulls back, and the shore is revealed to be a single grain of sand on a beach that runs past the horizon. Let me put some scale under the emptiness, because nothing out there is easy to say and hard to feel. The distances between the planets are already enormous, but they are distances your mind can just barely stretch to hold, because there are landmarks. Between the Sun and Neptune, there are worlds, moons, rings, a whole crowded neighborhood you can picture. The Oort cloud is different in kind, not just in size. It may begin a few thousand times the Earth-Sun distance out, and stretch to something like 100,000 times that distance, nearly 2 light-years, a spherical shell wrapped around the entire solar system. And inside that titanic volume, there is almost nothing. The comets are real, perhaps trillions of them, but they are spread so thinly across so much space that if you stood on one, the next one might be as far away as the Earth is from the Sun. You could fall through the Oort cloud for a human lifetime and never come within sight of a single object. It is less a cloud than a rumor of a cloud, a statistical haze of ice, so diffuse it barely deserves to be called a place. And that near-perfect emptiness is not a bug in the journey. It is the journey. When people imagine crossing space, they picture something like crossing an ocean, a hard passage, but a passage through something, with weather and waves, and the promise of a far shore. Space is not like that. The crossing is not hard, because space is full of obstacles. The crossing is hard, because space is almost entirely empty, and emptiness, in the quantities the universe deals in, is its own kind of wall. There is nothing to see, nothing to reach, nothing to break the distance into human-sized pieces. The very emptiness that ought to make space easy to move through is what makes it impossible to get anywhere, because getting somewhere means crossing all of it, and there is so unspeakably much of it to cross. Hold on to that idea, a barrier made of nothing, because it is going to come back later, wearing a very different and much more violent mask. And the truly frightening thing, the thing that should be sitting in your stomach as we go on, is that we have barely started zooming out. 2,500 years, and the fastest ship in history has gotten us only to the edge of our own sun's little pocket. The nearest other star is not twice as far, or 10 times as far. It is on the order of 1,000 times farther than everything we just crossed. Our real record holder, Voyager, flying for nearly 50 years, has not even covered a single light day, while the nearest star is more than 4 light years away. Think about that gap between a light day and a light year. Light itself, the fastest thing there is, takes a full day to cross the distance Voyager has needed half a century to travel, and then it takes more than 4 years beyond that just to reach the closest star. Our proudest, longest-running mission, the object that has flown farther than anything else we have ever made, has covered so little of the way that on the scale of the journey to even one neighbor, it rounds down to 0. 50 years of flight, and by the measure that counts, it has barely left the driveway. So the natural, human, stubborn response rises up, the same response that has served us at every rung of the ladder so far. If the distance is too big, then go faster. Just go faster. And it is exactly there, when we reach for more speed, that we run headfirst into the second wall, the one that does not care how clever we are. Because it is not a limit of our engines, it is a limit of the universe. Part 4. Why not just go faster? So we come to the obvious demand, the one every honest listener is already making. If the distances are too vast for 600,000 kilometers an hour, then stop playing with slingshots around Venus and go faster. Build a better engine, throw more money and more genius at it. We have doubled our speed before, many times over, all the way up this ladder, so double it again, and again, and again, until the distances finally give way. It is the response that has never once failed us in the whole history of travel. And it is about to fail us now, completely, and not because we are not clever enough. It is going to fail because of the way the universe is built at its foundations. And this is the second wall, and it is the strangest of the 4 to accept, because it feels like it should have a loophole, and it does not. There is a speed limit on the universe. It is the speed of light, and in empty space, that speed is about 299,792 kilometers every second, which works out to roughly 1 billion kilometers every hour. Now, the first thing everyone assumes when they hear about the speed of light is that it is just the current record, the fastest thing we happen to have measured, the way the sound barrier was once thought of as a wall until a plane punched through it. That assumption is wrong, and the wrongness is the whole point. The speed of light is not the fastest thing that happens to move. It is not a record waiting to be broken by a bolder pilot. It is built into the structure of space and time themselves, the deepest layer of how the universe is stitched together, and nothing with mass is permitted to reach it, not by us, not by anyone, not ever. Let me try to give you a feel for why, because it is one of the most beautiful and least intuitive results in all of physics. Space and time are not separate stages on which events happen. They are woven into a single fabric, and the speed of light is the exchange rate between them, the number that says how much space corresponds to how much time. When you speed up, you are not simply moving faster through a fixed backdrop. You are tilting the way you move through space and time relative to everything else. And as you push toward the speed of light, that tilt does something strange. The energy you pour into going faster stops translating cleanly into more speed. It starts translating into something else. It makes you harder to accelerate at all, as though the universe grows heavier in your hands the closer you get to the limit. This is the part that closes the door. To accelerate an object with mass, you have to give it energy, and ordinarily, a little more energy buys a little more speed. But as you approach the speed of light, that trade collapses. The same push buys less and less additional speed, because more and more of the energy goes into resisting the acceleration itself. To actually reach the speed of light, you would have to supply not a great deal of energy, not an enormous amount of energy, but an infinite amount of energy. And there is no infinite amount of anything available anywhere in the universe. The speed of light is therefore not a wall you hit. It is a horizon you can approach forever and never arrive at, no matter how much energy you burn, because the cost of the final step rises to infinity as you close in. And it is genuinely a wall, not a suggestion, because the alternatives that science fiction offers us are, so far, exactly that: fiction. A warp drive that folds space so you can cross it without moving through it quickly. A wormhole that punches a shortcut from one place to another. A way to teleport matter across the gap. A signal that outruns light. Physicists have taken all of these seriously enough to write the mathematics down, and the mathematics keeps demanding things that appear not to exist, like matter with negative energy, in quantities nothing in the observed universe can supply. And several of the schemes, if they worked, would let you send messages into your own past and unravel cause and effect entirely. None of these is a lie, exactly. They are honest placeholders for physics we do not have. But not one of them is a plan you could build, and betting the future of a species on them is betting on a door nobody has ever shown can be opened. There is a deeper reason this ceiling is not the villain it first appears to be, and it is worth planting now, even though we will not harvest it until the end. The speed of light is not only a limit, it is the reason the universe has any order at all. Because nothing can outrun light, cause always comes before effect, everywhere, for everyone. A thing that happens here cannot reach out and change something far away instantly. It has to send its influence across the gap, at light speed or slower, which means the universe has a settled sequence, a before and an after, that everyone agrees on within the limits the speed of light allows. Strip that ceiling away, and you do not get a faster universe. You get a universe where effects can precede their causes, where signals arrive before they are sent, where the very idea of a stable, consistent history dissolves. The wall that traps us is also the thing that keeps reality from tearing itself into paradox. Remember that. It matters later. And there is a strange gift buried in the ceiling too, one that seems, for a moment, like it might be our escape. As you approach the speed of light, time itself slows down for you relative to the universe you are crossing. A traveler moving fast enough could, in principle, cross enormous distances while barely aging, because their own clock runs slow. This sounds like a loophole, and people reach for it hopefully. But it snaps shut the instant you look closely, and it snaps shut because of the very next wall we are about to meet. To get meaningful time dilation, to actually cheat the years away, you have to fly terrifyingly close to the speed of light. And as we are about to see, flying that fast through real space, with its scattered atoms and dust, is not survivable at all. The faster you go to save time, the harder the universe hits you. The gift and the punishment are the same door. So sit with the shape of this second wall, because it is unlike anything in ordinary life. It is not that our engines are too weak. A stronger engine does not help. It is not that we lack a material, or a fuel, or a breakthrough that is surely just around the corner. The limit is not in the machine at all. The limit is in the road. The universe has posted a maximum speed, and it enforces that limit not with a barrier you crash into, but with a price that climbs to infinity as you approach. And there is no clever driver and no better car that gets around a price of infinity. And here is what makes it so much worse than it first sounds, the thing that turns this from an inconvenience into a cage. You do not get to fly right up against that limit for free. Long before you reach the speed of light, long before you get anywhere near it, a second price is already being charged, quietly, on every increase in speed. It is a tax written into the very definition of motion, and once you see it, you understand why even the physically possible engines, the ones that break no laws at all, still cannot save us. Part 5. The tax written into energy. The second price has a name in physics, and it is one of the first things you learn and one of the last things you truly feel. It is kinetic energy, the energy of motion, the energy a moving thing carries, simply because it is moving. And the crucial fact about it, the fact that quietly dooms so much of our hope, is how it grows. Kinetic energy does not grow in step with speed. It grows with the square of speed. That one word, square, is the tax, and I want to make sure you feel exactly what it does, because it sounds like a small technical detail, and it is actually one of the walls of the cage. Here is what squaring means in plain terms. If you want to go twice as fast, you do not need twice the energy. You need 4 times the energy, because 2 squared is 4. If you want to go 3 times as fast, you need 9 times the energy, because 3 squared is 9. 10 times as fast costs 100 times the energy. The price does not rise along a gentle ramp that matches your speed. It curves upward, steeper and steeper, so that every increment of extra speed costs more than the last one did, and the gap between what you have and what you need widens the harder you push. This is not a temporary shortfall in our technology. It is arithmetic. It is a term in the definition of energy itself, and there is no invention, no breakthrough, no genius that edits the exponent. 2 squared is 4 in every laboratory, on every planet, for every civilization that has ever existed or ever will. Now layer this on top of the way rockets actually work, and the trouble compounds into something almost cruel. A rocket moves by throwing fuel out the back. To go faster, it must throw more fuel. But that fuel has to be carried along until the moment it is burned, which means the rocket must also carry the fuel that will accelerate the fuel, and the fuel to accelerate that, and so the mass you need does not add up, it multiplies up. Engineers call this the tyranny of the rocket equation, and tyranny is the right word. To reach a modestly higher speed, you do not need a bit more fuel. You need exponentially more, until the fuel tank you would have to build dwarfs the ship, then dwarfs the planet, then becomes an absurdity. This is precisely why we resort to those elaborate slingshots around Venus in the first place. Brute force acceleration to high speed is so ruinously expensive that our mightiest rockets cannot afford even a taste of it. So let us ask the honest question, is there any energy source powerful enough to pay this tax, at least part way? And the honest answer is a careful yes. A yes with both hands raised in caution. There are energy sources that break no laws of physics and that pack far more punch than the chemical fuels we burn today. Nuclear fusion, the process that lights the stars, releases millions of times more energy per kilogram than burning kerosene. And beyond even that lies the annihilation of matter and antimatter, which converts mass directly and completely into energy, the most concentrated energy release the universe permits. In principle, on paper, a ship driven by fusion or by antimatter could reach a genuinely large fraction of the speed of light. Not the speed of light itself, that door is closed forever, but a real, meaningful fraction of it. The physics does not forbid this. It is, as far as we know, actually possible. And this is the moment I want you to hold, because it is the emotional hinge of the whole story. The place where the feeling changes from frustration into something colder and more permanent. Up to now, every obstacle has felt like a challenge, the kind of thing a clever enough species overcomes in time. Distance is a challenge. Weak engines are a challenge. But the squaring of energy is not a challenge. It is a law. It does not yield to effort, or to funding, or to a flash of insight in some future laboratory. It is not hard for now. It is hard forever, by the arithmetic of the universe. And there is a specific and lonely feeling that arrives when you understand that difference. When you realize that some walls are not waiting to be broken, but are simply part of the shape of what is real. The optimism you have carried since childhood, the sense that we will surely figure it out, quietly meets a number it cannot argue with. 2 squared is 4. It always was. It always will be. It helps to put a single hard number on how steep this tax really is. When physicists work out the kinetic energy of a spaceship at 20% of the speed of light, they find it carries an energy equal to a noticeable fraction of the ship's own mass converted entirely into energy, the full annihilation kind of energy, the kind the sun spends billions of years releasing. To accelerate a ship of any real size to that speed, and then, if you ever wanted to stop, to shed all of that energy again to slow back down, you would need to marshal an amount of power that beggars the entire output of human civilization. This is why proposals that take the physics seriously often abandon the idea of carrying people at all. One serious plan, sometimes called a light sail, imagines firing gram-sized probes, chips the weight of a paperclip, pushed by a gigantic array of ground-based lasers, precisely because a paperclip is light enough that even the squared energy tax becomes payable. The moment you insist on carrying a human crew, with their food and water and air and shielding, the mass climbs, the squared tax bites, and the numbers leave the realm of the possible. And notice the quiet trap in that light sail idea, because it foreshadows the wall that is coming. A laser can push a probe up to speed, but it cannot reach across 4 light years to push it back down again at the far end. A probe accelerated to 1/5 of light speed has no way to stop. It would flash through its target star system in a matter of hours, snapping a few photographs as it went, and then hurtle out the other side into deeper dark forever, unable to orbit, unable to land, unable to return. Even the plan that dodges the energy tax by staying tiny cannot afford to stop, because stopping costs exactly as much energy as starting did. The tax is charged twice, once to go and once to arrive, and almost every scheme that pays the first bill quietly gives up on the second. But let us not stop on despair, because that would be dishonest too, and this channel does not deal in easy despair. We said fusion and antimatter could reach a real fraction of light speed, so let us actually grant it. Let us be wildly, recklessly generous, more generous than any engineer would dare, and simply hand ourselves a ship that can fly at 20% of the speed of light. Not the speed of light, we know better now, but 1/5 of it, which is a staggering, almost unbelievable velocity. Let us assume we have paid the impossible tax somehow, waved the rocket equation away, and built the thing. Because I want to show you something important. I want to show you that even after we cheat, even after we grant ourselves a speed the tax should forbid, the cage still does not open. There are 2 more walls. And the next one is waiting in the one place you would swear was safe. It is waiting in the empty dark itself. Part 6. The Optimistic Ship. Let us enjoy this for a while, because we have earned a little hope, and the fantasy is genuinely thrilling before it turns. We now have a ship that flies at 20% of the speed of light. Let me put that speed in front of you, in real numbers, because it deserves to be felt. 20% of the speed of light is 60,000 kilometers every second. Not every hour, every second. It is 216 million kilometers every hour. Our old champion, the Parker Solar Probe, the fastest object our species ever built, managed something like 635,000 kilometers per hour, and we were rightly amazed by it. This new ship is more than 300 times faster than that. The pride we felt climbing the velocity ladder, the summit of 600,000 kilometers an hour, is now so far below us that it looks like standing still. This is the kind of speed that finally seems matched to the size of space. Remember that at every rung of the velocity ladder before this, the numbers climbed by comfortable multiples, and yet the distances always won. Now, for the first time, the speed has jumped by a factor so large that it feels like it might finally have caught up with the scale of the problem. We are no longer talking about being a little faster than our fastest machine. We are talking about being hundreds of times faster, a speed measured as a real fraction of the ultimate cosmic limit itself. And against a speed like that, surely the distances that crushed us must finally shrink to something a human life can hold. And watch what it does to the distances that just crushed us. The edge of the solar system, the outer Oort cloud, the boundary that took our fantasy ship 2,500 years to reach, we now cross in about 3.5 days. 3.5 days to cover a distance that a moment ago cost us 25 centuries. The whole vast emptiness we despaired over, the barrier made of nothing, we blow through it in less than a week. Push on, and the outer edge of the Oort cloud, the true last shore of the sun's domain, arrives in about 8 years. 8 years is a long expedition, but it is a human span, a thing a crew could actually live through, and at the end of it, you are genuinely, completely free of the solar system, out in open interstellar space, with a working ship and a living crew. For the first time all night, the door looks like it might be ajar. And then the real prize, Alpha Centauri, the nearest star system to our own, the closest other sun, with the closest other worlds, sits about 4 1/3 light years away. On a slow, realistic ship, it is a journey of many thousands of years, an impossibility dressed as a destination. But on our 20% of light speed ship, Alpha Centauri is about 20 years away. 20 years. Cram a small crew into a well-built vessel, send them off as young men and women, and they arrive in middle age at another star. People have given 20 years to far smaller things. A war, a career, the raising of a child, a prison sentence. 20 years to reach another sun, to be the first living things from Earth, to cross the gulf between the stars, suddenly does not sound like a fantasy at all. It sounds like something a determined civilization might actually choose to do. There is one shadow already falling across even this good version, and honesty requires naming it before we go on, because it never really lifts. At 20% of the speed of light, the time-slowing effect we spoke about earlier is almost nothing. It only becomes powerful very close to light speed, and 1/5 of the way there barely bends the clock at all. So the crew that takes 20 years to reach Alpha Centauri genuinely lives 20 years to do it. They are not stepping out of time. They are spending 2 decades of their actual lives, watching everyone they left behind grow older in near lockstep, and then, when they arrive and send word home, their message itself crawls back across the gulf at the speed of light and takes more than 4 years to be heard. A conversation with home would have a lag of nearly 9 years between question and answer. Whatever they build out there could never be part of a living, responsive human civilization. It would be an island, cut off by the very distance it crossed, hearing news from Earth that was already ancient by the time it arrived. So even the beautiful version has a coldness at its center. But set that aside for now, because it is a sorrow, not a wall, and we are here for the walls. Let us grant the crew their willingness to be an island. Let us assume they make peace with the isolation, the lag, the one-way character of the whole enterprise. Plenty of explorers in history left everything behind, knowing they would never return, and perhaps ours would too. The isolation does not stop the ship. It only breaks the hearts aboard it. The thing that actually stops the ship is something else, something physical, something waiting in the space ahead, and to that we now have to turn. So let us sit in the good version of the story for a moment, because it is worth honoring before it breaks. In this version, the distance problem is beaten, not by magic, but by a real, physically permitted speed. The light speed wall still stands, but we did not need to touch it. We only needed 1/5 of the way there. The energy tax was brutal, but we imagined a source, fusion, or antimatter that could in principle pay it. And with all of that granted, the nearest stars come within reach of a single human lifetime. This is the future we were promised as children, the one that felt inevitable, and here, in this generous fantasy, it very nearly comes true. You can almost see the ship pulling away from Earth, the crew waving, the long patient years of the crossing, the first grainy message home from another star. It is beautiful. Hold that picture, because I am about to take it apart, and I want you to remember how close it looked. Because there is a catch, and it is not a small one, and it is hiding in a place so ordinary that we sailed right past it. We have been treating the space between the stars as if it were truly empty, a perfect vacuum, a clean track our ship glides through without resistance. That picture is wrong. Space is very empty, emptier than anything you have ever experienced, but it is not actually empty, and the difference between very empty and actually empty is about to become the difference between a living crew and a wreck. There are things out there in the dark between the stars. Not many, almost none by the standards of a room full of air, but they are there, scattered thinly through the void, and at 20% of the speed of light, running into almost nothing, turns out to be one of the most violent things that can possibly happen to you. The emptiness we thought was our friend is the third wall, and it has been waiting for us to go fast enough to feel it. Part 7. Step back and stack the pieces. Let us stop here, roughly halfway, and put the pieces on the table where we can see them all at once, because the story has been building quietly, and it is worth feeling the weight of what we already know before we add the last of it. This is the moment to breathe and take stock, the way you might pause on a long walk to look back at how far the path has climbed. There is a real value in doing this, in stopping to restack the pieces, and not only because it helps anyone who has drifted a little. It is because the walls we have met were introduced one at a time, and any single one of them, on its own, sounds like the kind of thing a determined species eventually beats. It is only when you set them side by side, all at once, on the same table, that you begin to feel the shape they make together. So let us lay them out deliberately, in order, and see the whole board before we add the final piece. We started with a promise that we could go anywhere, because nothing is holding us down. There is no ceiling over our heads, no leash from the sun, and we proved it, because a probe from the 1970s has already broken free of the sun's gravity and is drifting outward forever. So the thing that traps us is not a force. That was the first thing we set down. Whatever the cage is, it does not pull. Then we picked up speed, the thing that crosses distance, and we climbed the ladder of our fastest machines, all the way to the Parker Solar Probe at more than 600,000 kilometers an hour, and we felt proud. And then we zoomed out, and the pride evaporated, because at that fastest ever speed, the edge of our own solar system is still 2,500 years away, and there is nothing there when you arrive. That was the first wall, distance, a barrier made of nothing but how much nothing there is. So we reached for more speed, and we hit the second wall, the speed of light, which is not a record, but a ceiling built into the fabric of space and time, unreachable at any finite energy. And pressed against that ceiling, we found the third pressure, the tax, the way energy grows with the square of speed, so that going faster costs not a little more, but exponentially more, a price no cleverness can lower, because it is written into the definition of motion itself. Those are the pieces, no leash, but a wall of distance, a ceiling of light, and a tax on speed. And here is the strange thing, the thing that should make you lean forward rather than sink back. Even with all of that stacked against us, we found a door. We granted ourselves a ship at a fifth of the speed of light, a speed the physics permits, even if our engineering does not. And suddenly the numbers turned kind. The edge of the solar system in 3.5 days. Open interstellar space in 8 years. The nearest star in about 20. A human lifetime, spent, but spent successfully. On paper, in this generous fantasy, the cage has a way out. The distance is beaten, the light ceiling is never touched, and the energy tax, though brutal, we simply imagined paying. By every measure we have examined so far, the trip is possible. And notice something about the way these pieces fit, because it is the shape of the argument tonight, and it is worth naming out loud. Each wall we have met, taken entirely on its own, could be survived. The distance alone, if that were the only problem, could be beaten by patience, by a slow ship, and a long enough journey, if only there were nothing else in the way. The light speed ceiling alone does not actually trap us, because we do not need light speed, only a fraction of it, and a fraction is enough to reach the nearest stars in a lifetime. The energy tax alone might be paid by a civilization far richer and more advanced than ours, one that had learned to harness fusion or antimatter at a scale we can barely imagine. Any one of these three, by itself, has a way through. That is the crucial and easily missed fact. The walls are not individually impassable. If the universe had built only one of them, we would already be among the stars. The trap is not in any single wall. The trap is in the way they are joined, and we are about to add the fourth, and the fourth is the one that reaches across and locks the others together, because it turns the solution to one wall into the trigger for another. Watch for that as we go on. Watch how beating the distance, by going fast, is the very thing that arms the emptiness against us. The cage is not 4 separate bars. It is 4 bars welded into a single shape, and the welding is the reason. So what is the catch? That is the honest question hanging in the air right now, and you can feel that there must be one, because I promised you 4 walls, and we have only truly met 3, and because the whole title of tonight insists that we can never leave. We have a ship, we have a speed, we have a destination 20 years away. Every obstacle we have named, we have found a way around or through. If the story ended here, it would end in hope, and it does not end in hope, which means something is still waiting. Take one more moment with the strangeness of the situation before we go on, because it really is strange. We have, in this fantasy, everything a dreamer could ask for. We have beaten the distance with a real, physically permitted speed. We have left the light speed ceiling untouched, needing only a fraction of it. We have imagined an energy source, fusion or antimatter, that pays the terrible tax. Every named obstacle has an answer, and yet the title of tonight still insists, flatly, that we can never leave, and I have promised you it is right. That gap, between a journey that looks entirely possible on paper and a conclusion that says it is impossible in fact, is where the last wall lives. It is not a wall you would ever think to check for, because it hides inside the one thing we have been treating as safe and simple and empty this entire time. And it is waiting in the last place you would think to look, not in the engines, not in the distance, not in some exotic law of physics. It is waiting in the emptiness itself, in the very vacuum we have been treating as a clean and harmless road. We assumed that the space between the stars, being nearly empty, would simply let us pass. That assumption is the 4th wall, and it is the one that finally closes the cage, because at 20% of the speed of light, nearly empty is not the same as empty, and the difference between them is measured in fire. Let us go and meet the thing in the dark. Part 8. Space is not empty. We have been telling ourselves a small lie for this entire journey, an understandable one. The same lie everyone tells when they picture space travel. We have been imagining the vacuum between the stars as truly empty, a perfect nothing, a clean black track our ship glides through without touching a single thing. It is almost true. It is so nearly true that for slow travel it might as well be true. But it is not actually true, and the gap between almost empty and actually empty is where the 4th wall lives, and it is the wall that finally closes the door for good. Here is what is really out there in the dark, between the stars. It is not truly a void. It is a thin haze of gas and dust, the interstellar medium, the leftover breath of dead stars spread across the enormous distances. In the particular cloud of it that our sun is drifting through right now, there is roughly 1 hydrogen atom in every 3 cubic centimeters of space, and across the galaxy as a whole, the average is something like 1 atom per cubic centimeter. Let that sink in for how empty that is. A single atom in a space the size of a sugar cube. Compare that to the air you are breathing, where every cubic centimeter holds tens of billions of atoms, and you see that the interstellar medium is a vacuum so profound that no machine on Earth can produce anything close to it. It is, by every ordinary standard, nothing at all. And at walking pace, or at the pace of a car, or even at the pace of the Parker Solar Probe, that nothing is exactly as harmless as it sounds. You could drift through it for 1,000 years and never notice the occasional atom brushing past. But now remember how fast our ship is going, 60,000 kilometers every second. And remember the tax we learned about, the way energy grows with the square of speed. Those two facts, the thin scattering of atoms and the enormous speed, are about to multiply together into something monstrous. Because it does not matter how few the atoms are if you are slamming into each one at 1/5 of the speed of light. Think carefully about what a collision even means here. When your ship, moving at 60,000 kilometers a second, meets a single hydrogen atom hanging in space, from the ship's point of view, it is not the ship that hits the atom. It is the atom that comes screaming in and slams into the hull at 1/5 of the speed of light. And an atom moving that fast is not a gentle speck. It is a bullet. In fact, it is more than a bullet, because at these speeds, a single atom carries the kind of energy that physicists normally only reach inside the giant machines they build to smash particles apart. A lone hydrogen atom arrives with millions of electron volts of energy. A heavier atom, an iron atom, arrives carrying more than 1 billion electron volts, the energy of a particle in a laboratory's beamline, except this beamline is the entire sky ahead of you, and it never switches off. It is worth being precise about why speed does this, because it is the same tax we met before, wearing a new and frightening face. The energy a moving thing carries grows with the square of its speed. An atom drifting slowly through space carries almost no energy at all. That same atom, meeting a hull at 1/5 of the speed of light, carries an amount of energy set by that squared relationship, and 1/5 of light speed is so enormous that even a single hydrogen atom, the lightest thing there is, arrives with the punch of a subatomic bullet fired from a laboratory machine. This is not a special or exotic effect. It is the ordinary physics of kinetic energy, the very same law that made our rocket fuel multiply out of control, now turned against us from the outside. The faster we fly to beat the distance, the more energy every stray atom carries when it hits us. Speed is not a way around the medium. Speed is what loads the medium's gun. And there is a second cruelty layered on top. These atomic impacts do not only pit the hull, many of them are energetic enough to drive deep into the material and to knock loose showers of secondary particles, a burst of radiation blooming inward from every strike, the same kind of ionizing radiation that damages living cells and scrambles the delicate electronics a ship depends on. So the crew is not only riding inside an eroding hull, they are bathed continuously in a haze of radiation generated by their own motion through the thin gas of space, a dose that accumulates without pause across every year of the crossing, degrading the shielding, the machines, and the bodies of everyone aboard, all at once. What does that do to the ship? It means the hull is being sprayed, constantly, every second of every day of the entire voyage, with a fusillade of atomic bullets, each one burying itself a fraction of a millimeter into the material and leaving a tiny track of damage where it tears through. One atom does nothing you would notice. But there is no such thing as one atom out here. There is a continuous rain of them, trillions upon trillions over the years of the crossing, and slowly, relentlessly, they carve the leading face of your ship, full of microscopic holes. The hull does not fail all at once. It is eroded, sanded down from the front, riddled like old wood full of worm tunnels, growing thinner and more brittle with every light year, and the faster you fly to shorten the trip, the harder and more energetic that rain becomes. And here is a further turn of the knife, one that removes even the comfort of a steady, predictable danger. The density of the medium is not the same everywhere. Right now, our sun happens to sit inside an unusually empty pocket of the galaxy, a region swept clean by ancient exploding stars, where the gas is even thinner than the galactic average. That is a stroke of luck for us, but it is a local stroke of luck, a temporary address. Aim your ship at a distant star, and your path will not stay in this clean pocket. It will cross into denser clouds, regions where the gas and dust are packed hundreds or even thousands of times more tightly than the sparse haze around us. In those clouds, the rain of atoms is not a whisper but a torrent, and the odds of meeting a lethal grain climb accordingly. The map of interstellar space is not a uniform calm. It has weather, and some of the weather is far deadlier than anything near home, and you cannot see it coming until you are already flying through it at a fifth of the speed of light. So the emptiness we crossed in the first half of this video, the emptiness that seemed like mere distance, turns out to have teeth. At low speed it is harmless and merely vast. At high speed it becomes an active hazard, whose severity you cannot fully know in advance, that erodes you continuously, irradiates you continuously, and hides, somewhere along your path, the one grain or the one pebble that ends everything. And this is only the atoms, the smallest things in the dark, the gentlest of the hazards. The engineers, of course, anticipated this, and they built a shield, a thick protective barrier, or a great sacrificial sail mounted on the front of the ship, designed to soak up the rain of atoms and slow whatever it can before it reaches the crew. And against the atoms, a good shield might just hold. But the atoms are not the only thing floating in the void. There are bigger things out there. There is dust, and running into a grain of dust at 20% of the speed of light is not like being sprayed with atomic bullets. It is like driving into a bomb. Part 9. The Wall of Dust. Stand with me, in your mind, just behind the forward shield of the ship, and let us watch the dark come at us at a fifth of the speed of light. You cannot see the atoms. They arrive as a faint, ceaseless whisper of energy deep in the shield material, a warmth that never fades, individual needles of motion burying themselves silently by the trillion. For a while it is almost peaceful, this quiet erosion, this steady hiss of the vacuum grinding against the hull. And then a single mote of dust, a speck so small you would never see it on your fingertip, crosses the ship's path. There is a flash, a hard, silent flash of light, and a tiny crater blooms in the face of the shield, and a puff of vaporized material trails away behind you into the dark. The dust grain did not scratch the shield, it detonated against it. Its flash evaporated in an instant, releasing its energy like a small bomb, and it took a little piece of your only protection with it as it went. Understand what just happened, because it is the heart of the fourth wall. A grain of dust is a nothing, a mote, a thing that drifts unnoticed through the air of your home by the millions. But at 20% of the speed of light, that mote carries so much kinetic energy that when it stops against your shield, all of that energy has to go somewhere in an instant, and what it does is explode. The grain evaporates, the shield surface around it evaporates with it, and a tiny nuclear-sharp burst of heat and light marks the spot. One grain, one small crater, one puff of lost shielding. That is survivable, once, but the void is not empty, and there is not one grain. There is a slow, endless scattering of them along every light year of the way, and each one that finds you carves away a little more of the barrier, keeping the rain of atoms off your crew. The shield is not being scratched, it is being sanded away from the front, one tiny detonation at a time, and it cannot be replaced in flight. And the dust is not the worst of it, because out there in the same dark, far more rarely, there are things bigger than dust. A pebble, a chip of rock, the size of a golf ball, 50 grams of ordinary stone, the kind of thing you would skip across a pond without a thought. Do the arithmetic on that pebble at a fifth of the speed of light, and the number that comes back does not feel real. A 50-gram pebble, struck at that speed, releases an amount of energy comparable to the atomic bomb that was dropped on Hiroshima. By some estimates, more than double it. Not a crater, not a puff of vaporized shielding, a nuclear detonation against the front of your ship, from a rock you could hold between 2 fingers. There is no shield that survives that. There is no material, no design, no cleverness that lets a crude vessel absorb the energy of a nuclear weapon delivered by a stone and keep flying. If your ship meets 1 golf ball pebble in 4 light years of dark, the voyage is simply over, in a flash, with no warning and no defense. And there is no simple engineering answer waiting in the wings, no matter how much armor you imagine bolting on, because of the tax we keep returning to. Every kilogram of shield you add is another kilogram you must accelerate to a fifth of the speed of light, and the energy cost of that acceleration grows with the square of the speed, so a heavier shield means a vastly more expensive ship, which means even more fuel, which means even more mass. The very protection you need to survive the medium makes the energy problem worse, and the energy problem was already at the edge of the impossible. You cannot simply out-armor the void. Past a certain point, adding shielding costs more than it saves, and you are left with a ship that is mostly shield and fuel, wrapped around a tiny, fragile crew, still being eroded from the front, still 1 pebble away from a nuclear flash. The engineers who have looked hard at this do not come away with a design. They come away convinced there may be a natural speed limit for matter moving through real space, set not by our engines but by the dark itself. Some proposals try to soften the blow with a great sacrificial sail flung out ahead of the ship, a thin sheet of material meant to absorb or deflect the worst of the rain before it reaches the vessel. And it helps, a little, against the atoms and the smallest dust. But a sail is exactly the wrong thing to put in front of a golf ball pebble, because the pebble does not care about a thin sheet. It carries the energy of a nuclear bomb, and a sheet of foil in its path simply becomes part of the explosion. The sail buys you protection against the things that were only going to erode you slowly. It buys you nothing against the rare thing that was going to kill you instantly. And across 4 light years, or 40, the odds of meeting that rare thing climb with every kilometer. This is the moment the whole fantasy inverts, and I want you to feel the inversion, because it is one of the strangest things in all of physics. We spent the first half of tonight afraid of how empty space is. The emptiness was the enemy. It was the emptiness that made the distances so vast, the emptiness that took 25 centuries to cross, the barrier made of nothing. And now, at high speed, that exact same emptiness has turned into the opposite kind of enemy, the near-perfect vacuum. The thing that ought to make space the easiest possible thing to move through has become a shooting gallery. The handful of atoms and grains and pebbles scattered through the dark, so sparse that at any slow speed they are utterly harmless, become at a fifth of light speed a continuous barrage of bullets and bombs. The emptiness did not save us. The emptiness, multiplied by our own speed, is what kills us. There is a particular horror in the manner of it too, that is worth sitting with for a moment. The pebble gives no warning. At a fifth of the speed of light, you are moving so fast that nothing your instruments could detect gives you time to react. Light from the pebble, the first hint of its existence, arrives only a fraction of a heartbeat before the pebble itself, because you are closing on it at a fifth of the speed of the very light that would announce it. There is no alarm, no chance to steer, no dramatic final moment. The crew would not know. One instant the ship is flying, the long patient years of the voyage unspooling as they always have, and the next instant there is no ship, only an expanding flash of light and vapor where a vessel and its people used to be, marking the spot where a stone the size of a golf ball happened to be waiting in the dark. And nobody at home would learn of it for years, if ever, because the light of that flash would take just as long to crawl back across the gulf as the ship took to cross it. So look at the box we are in now, because it has become airtight. Go slow, and the distance defeats you. The nearest star is thousands of years away, at any speed we can really build, and no crew and no civilization survives a journey measured in millennia through the empty dark with nothing to sustain it. Go fast, and the medium defeats you. The very speed that beats the distance turns the thin scattering of the vacuum into a wall of radiation and micro-explosions, and, eventually, one unlucky pebble that ends everything in a nuclear flash. There is no speed that is both fast enough to cross the distance and slow enough to survive the crossing. The two lethal limits do not leave a gap between them, they overlap. Whatever speed you choose, one of them is waiting, and that overlap, that closing of the two jaws, is the trap taking its final shape. And once you see that the trap is made of a relationship, and not of any single wall, the true strangeness of the reason finally comes into view. Part 10. The Strange Inversion. I want to slow all the way down here, because we have arrived at the strangest idea in this whole story, and it is the one that changes how you see everything we have covered. It is the reason I called this a strange reason, and not simply a hard one. Because if you asked most people what stands between us and the stars, they would picture an obstacle, a thing, a barrier you could point at, a wall. And what we have actually found is not a wall at all. What we have found is a relationship, and relationships are much harder to fight than walls, because there is nothing to push against. Consider what the emptiness of space has done to us over the course of this video. In the first half, when we were moving slowly, the emptiness was the enemy because it was so vast. It was pure distance, a barrier made of nothing, 25 centuries of black, to reach the edge of our own sun's territory. The problem was that there was too much nothing, so we did the only sensible thing. We went faster, to cross all that nothing more quickly, and in going faster, the very same nothing, the identical thin scattering of atoms and dust we had been ignoring, transformed into a wall of fire. The emptiness did not change. Not one atom moved. What changed was our speed, and our speed turned the harmless void into a lethal one. The same emptiness, at low speed a barrier of distance, at high speed a barrier of violence. Sit with how strange that is. The obstacle is not the atoms. The obstacle is not our speed. The obstacle is the relationship between them, the product of the two, and you cannot remove a relationship by engineering, because it is not a thing that exists in any one place. Slow down to make the medium harmless, and the distance becomes lethal instead, because now the journey takes longer than any crew or civilization could endure. Speed up to beat the distance, and the medium becomes lethal, because now every atom is a bullet, and every pebble a bomb. There is no dial you can set that makes both problems small at once. Turn the speed down, and one jaw of the trap closes. Turn the speed up, and the other jaw closes. The gap you are looking for, the speed that is fast enough to cross the distance in a lifetime, but slow enough to survive the crossing, does not exist. The two lethal zones overlap, and the overlap is complete, and that is the cage. And this coupling is why the trap is so much more stubborn than an ordinary problem. When engineers face a normal obstacle, they can attack it directly, pour resources at the single thing standing in the way until it gives. But you cannot pour resources at a relationship, because there is no single thing to attack. Make the ship faster, and you have not removed the medium, you have made it deadlier. Slow the ship down to spare it from the medium, and you have not shortened the distance, you have made the journey longer than any life. Add armor against the dust, and you have made the ship heavier, which makes the energy tax worse, which makes the whole thing more impossible than before. Every lever you can pull is connected to every other lever, and pulling one to ease one wall tightens another. The problem has no loose end to grab, no single weak point to break, because its strength is not in any part, but in the way the parts are tied together. This is what I mean when I say the barrier is made of nothing. I mean it almost literally. There is no substance to it. If you flew out into interstellar space and stopped and drifted, you could hold out your hand and feel nothing, see nothing, meet nothing, for years. The barrier is not present as an object anywhere along the route. It only appears when you try to cross quickly, and it appears not from some new thing entering the scene, but from the interaction between your motion and the near-perfect vacuum that was always there. It is a barrier that is invisible and absent right up until the instant you need to move through it fast, and then it becomes the most solid thing in the universe. A wall you cannot see, cannot touch, cannot locate, and cannot survive. And notice that this is why every clever escape we have imagined fails in the same way. Each one opens one lock and leaves the others shut. The fusion drive pays down the energy tax, a little, but it does nothing about the medium. The laser sail dodges the energy problem by staying tiny, but a tiny probe still cannot stop at the far end and still meets the same dust. Suspended animation could let a crew endure the years, but the ship still has to survive the crossing intact, pebbles and all. Extend human lifespans to centuries, and you have made the distance bearable, but done nothing about the wall of fire that a fast ship runs into. Every single proposal is a key that fits one lock. Not one of them is a key that fits all four at once, because the locks are wired together, and turning one arms another. This is the deep structure of the trap, and it is why it does not feel like the sort of problem a century of progress simply solves. It is not a gap in our knowledge. It is a property of the way distance, light, energy, and matter are related to one another in this universe. And there is a consequence of this that reaches far beyond us, one that quietly reframes one of the oldest questions we ask about the sky. If the cage is made of physical law rather than of our particular weakness, then it is not our cage alone. It fits everyone. Every carbon-based creature that has ever evolved on any world around any star faces the exact same four walls, because the speed of light is the same everywhere. Energy grows with the square of speed everywhere, and every interstellar medium becomes a wall of fire at a fifth of light speed everywhere. There may be millions of civilizations scattered through the galaxy, each one looking up at its own night sky, each one dreaming the same dream of crossing to the stars, and each one held in place by the same physics that holds us. Not one of them able to venture out in any meaningful, lasting way. Not one of them able to build the great, connected, star-spanning empire that our stories take for granted. People have wondered for a long time why the galaxy seems so quiet. Why, if life is common, we have not been visited or hailed or colonized. There are many possible answers, and this is only one of them, but it is a sobering one. Perhaps the great silence is not because life is rare, and not because civilizations destroy themselves, but simply because the laws of motion do not permit anyone to leave home in a way that matters. Perhaps the quiet is the sound of a universe full of minds, every one of them trapped in its own solar system by the same four walls, all of us waving at each other across distances that the physics forbids us ever to cross. The cage, if it is real, is not a local misfortune. It may be the universal condition of everything alive. So we could almost stop here, with the cage fully described, four coupled walls that no living thing can pass. But I promised you at the very beginning that this was not, in the end, a sad story, and I meant it. Because there is one more question to ask about these four walls, and it is the question that turns the whole thing over and shows you its other face. We have been asking what the walls do to us. We have not yet asked where the walls come from. And when you finally ask that, when you look at each of the four bars of the cage and ask why the universe has that particular bar at all, you find something that I honestly did not expect when I first went looking, something that makes the trap feel less like a prison and more like the shape of a home. Let us ask it. Let us ask where the cage comes from. Part 11. And the far end is a letdown. Before we turn the cage over and look at where it comes from, there is one more cruelty to face, and it is the one that hurts in a different way than all the physics. Everything so far has been about whether we can survive the crossing. Let us set that aside for a moment and grant, generously, impossibly, that somehow a ship makes it. It threads the medium, it dodges the pebbles, it pays the energy tax, it carries a crew safely across the years. Suppose all of it works. The question that remains is the quietest and the most deflating of the whole night. When you finally arrive, is there anything there worth the journey? And the honest answer, for almost everywhere we could actually reach, is no. Let us look at the neighborhood, the small sphere of space around our sun that a fast ship might reach within a human lifetime or two. Draw a bubble about 25 light-years across, centered on us. That sounds generous, and in human terms it is enormous, but set against the galaxy, it is almost nothing, about 0.02% of the Milky Way, a single dust mote in a cathedral. And inside that bubble, inside our entire reachable neighborhood, there are only a few dozen stars, and a scattering of dim, failed stars called brown dwarfs that never quite caught fire. That is the whole inventory, a few dozen suns, and most of them are nothing like our own. The great majority of the stars near us are red dwarfs, small, cool, dim stars, utterly unlike the sun, and the planets around them are, as far as we can tell, a spectrum that runs from deadly to more deadly. Red dwarfs are prone to violent flares that would strip the air and scorch the surface of any world close enough to be warm. The planets that do sit in the narrow zone where water could be liquid are usually so close to their dim star that they are tidally locked, one face baked in eternal day, the other frozen in eternal night. Out of all the stars in our reachable neighborhood, only a small handful even loosely resemble the sun, and one of those, remember, is the sun. Another is one of the stars of Alpha Centauri. The pickings, for a species looking for somewhere to actually live, are astonishingly thin. And here is the specific heartbreak, the thing I keep coming back to. Even the very best nearby candidates, the exoplanets that get written up as the most Earth-like worlds we have found, come with no guarantee of being anything but another dead rock. There is a world about 12 light-years away, orbiting a red dwarf, that turns up on lists of potentially habitable planets. But potentially is carrying an ocean of doubt. We call a planet potentially habitable if it merely sits at the right distance for liquid water, and by that same loose standard, Mars, our own frozen, airless, radiation-blasted neighbor, sits in the sun's habitable zone too. Mars is in the habitable zone, and Mars would kill you in minutes. So when we say a distant world is potentially habitable, we may be saying nothing more than that it is potentially another Mars. It is worth pausing on why the nearby stars are so overwhelmingly the small, dim, difficult kind. Because it is not bad luck. It is simply the way stars are made. The universe produces far more small stars than large ones. For every bright, steady, sun-like star, there are many more feeble red dwarfs. So when you draw a bubble around any random point in the galaxy, including ours, the overwhelming majority of what you catch will be these dim red stars. And a red dwarf is a difficult host for life. It is so cool that a planet must huddle close to stay warm, and huddling close means the planet is likely locked with one face always toward the star, and it means the planet sits right in the firing line when the red dwarf throws one of its violent flares, which it does often, blasting the little world with radiation that can strip away an atmosphere over time. The nearby galaxy is not stocked with gentle twins of our sun waiting to be settled. It is stocked, mostly, with small angry stars and their scorched or frozen or tide-locked worlds, and that is the ordinary, typical furniture of the Milky Way, not some special misfortune of our address. Now put yourself in the story, because this is the emotional heart of it. Imagine you are one of the crew. You gave your entire life to this, decades sealed in a metal room, watching through a lagging, years-old feed, as everyone you loved back home grew old and died while you flew. You endured the isolation, the confinement, the slow radiation, the constant low terror of the dark outside, and at last the ship decelerates, and the new world swings into view, in the window, the world you crossed an ocean of night to reach, and it is a Mars, a frozen desert, or a baked and airless rock, or a flare-scorched cinder locked to its dim red star. You traveled your whole life, and everyone's whole lives, to arrive at another lifeless stone. That is not fear, that is grief, a specific and terrible grief, and it is the grief the physics keeps promising, because the universe has arranged things so that the places we can reach are precisely the places least likely to be worth reaching. And even if you reached one of the rare good worlds, the distance would still have the last word, in a subtler way. A colony 4 light-years away could never be part of a living human civilization. A message from home would take more than 4 years to arrive, and the reply more than 4 years to return, so every conversation would span nearly a decade. News, help, ideas, the ordinary back and forth that makes a civilization a single connected thing, would all crawl between the stars at the speed of light and arrive already old. A settlement out there would not be an outpost of humanity so much as a lonely seed, cut off at the moment of planting, growing, or dying entirely on its own, hearing from the world that made it only in fragments from the deep past. The distance does not merely make the journey hard, it severs anything you might build at the far end from everything you left, permanently, by the same speed of light limit that capped the ship. This is why the grander schemes people propose, the generation ships that would carry not a crew but a whole travelling society across the centuries, the vessels that would launch with frozen embryos to be raised by machines at journey's end, do not really escape the problem so much as rename it. They are ways of enduring the distance, not of defeating it, and every one of them still has to survive the crossing, still has to thread the medium, still arrives, most likely, at another Mars, still ends up as an island, cut off from home by years of lag. They convert the physical cage into a multi-century engineering and human problem of staggering difficulty, and even if all of that were solved, the destination and the isolation would still be waiting. The walls do not fall. They only get papered over with heroic amounts of patience. There is a final twist to this arrangement, and it is almost too perfect to be an accident, though it is. The genuinely wonderful destinations, if they exist, the worlds with real oceans and breathable air, and the near certainty of life, are almost certainly not in our reachable neighborhood at all. They could be dozens of light years away, or hundreds, or thousands. And that means journeys not of 20 years, but of centuries or millennia, even at a fifth of the speed of light, straight back into the teeth of every wall we have described. So the universe sorts itself with a cruel neatness. What is close is not worth reaching. What is worth reaching is not close. The reachable is lame, and the wonderful is unreachable, and the line between them is drawn by the same physics that built the cage in the first place. Which brings us, at last, back to that physics, and to the question I promised would turn this whole story over. Where do these 4 walls actually come from? Why does the universe have them at all? Part 12. The cage is made of the laws that made you. So let us finally ask the question I have been saving all night. Where do the 4 walls come from? Not what they do to us, we know that now, but why the universe has them at all. And when you go looking, one at a time, you find something I genuinely did not expect the first time I followed this thread. Something that turns the whole feeling of this story inside out. Every single one of the four walls that traps us is also, at the same time, a thing without which you could not exist to be trapped. The bars of the cage are the beams of the house. Let me show you, slowly, because this is the part worth staying awake for. Start with the speed of light, the ceiling we can never reach. Feel what it is actually doing right now, this very second, inside your own chest. Because nothing can travel faster than light. Cause always comes before effect, everywhere. And the universe has a settled, consistent order in which things happen. The atoms in your body hold their arrangement from one moment to the next, because the forces between them propagate in an orderly way, at or below that same speed, so that the pattern that is you stays stable, stays itself, second after second after second. Strip that ceiling away, and you do not get a faster universe. You get a universe with no reliable before and after, where effects outrun their causes, and the delicate, persistent pattern that is a living body could never hold together at all. The wall that keeps you from the stars is the same wall that keeps you from dissolving. It is the reason there is a you that lasts long enough to have this thought. There is something almost tender in that, when you let it land. The thing that forbids you the stars is the same thing that grants you the next second of your own continued existence. A universe without that ceiling might, in some story, let a ship fly faster, but it would be a universe in which nothing stayed itself long enough to fly anything. A universe with no stable patterns, no atoms holding their shape, no bodies, no minds, no travelers to be disappointed by the limit. The ceiling is not an obstacle placed in the way of life. It is one of the conditions that makes a persisting, remembering, wondering life possible in the first place. You cannot have the kind of universe that grows a you, and also have the kind of universe that lets that you outrun light. They are not two separate wishes. They are the same wish, and it was granted. Now take the second wall, the one that turned dust into bombs, the fierce grip of the electromagnetic force at high speed. That force, the one that makes a grain of sand detonate against a ship at a fifth of light speed, is not some alien danger. It is the very same force that binds atoms into molecules, that holds your cells together, that lets your hand close around a cup and your eyes turn light into sight. The electromagnetic force is what makes matter solid, what makes chemistry possible, what makes a body instead of a diffuse cloud of particles. It is only lethal to a starship because it is so strong, and it is so strong precisely because it is doing the work of holding all ordinary matter, including you, together. The force that would shatter the ship is the same force, at gentler speeds, that is holding your hand together as you rest it on your chest right now. Take the third wall, the energy tax, the way the cost of speed grows with its square. That relationship is one face of the deep conservation laws that govern how energy moves and is accounted for in this universe, the same bookkeeping that makes the sun burn steadily and slowly, pouring out its light at a measured pace across billions of years rather than detonating all at once. If energy did not obey these strict and unforgiving accounts, stars could not shine gently and long. And it took the sun's long, patient, well-behaved burning, 4.5 billion years of it, to warm the earth steadily enough for oceans to settle and life to begin, and a species to slowly wake up and look at the sky. The tax that makes your starship impossible is a face of the same law that made your star reliable enough to grow up under. Think for a moment about what a crowded galaxy would actually be like, the kind with stars packed close enough that the distances between them were small and easy to cross. It sounds, at first, like exactly the universe we wish we had, a sky full of near neighbors, a short hop away. But a sky like that would be a catastrophe for life. Stars that near would tug at one another constantly, flinging planets out of stable orbits, raining comets down on any world that tried to settle, bathing everything in the radiation of too many nearby suns, colliding and merging and churning the whole neighborhood into chaos. No planet could hold a calm, circular orbit for the billions of years that life requires. The very closeness that would make travel easy would make the worlds themselves uninhabitable. And take the fourth wall, the sheer, crushing vastness of the distances, the emptiness that took 25 centuries to cross. Why is space so empty, the stars so far apart? Because if they were not, if stars were packed close together, they would constantly disturb one another, fling planets out of their orbits, bathe every world in too much radiation, collide and merge and destroy the long, quiet stability that a planet needs to hold a stable orbit for the billions of years it takes life to arise. The enormous empty distances between the stars, the very distances that trap us, are the reason our own solar system could sit undisturbed in a calm, empty pocket long enough for a planet to cool, an ocean to gather, a cell to form, a mind to wake. The emptiness that is our prison is the emptiness that was our cradle. It kept the neighborhood quiet enough for us to be born. Let me ask you to do something with your body while you listen, because this is a thing better felt than argued. Lie still, wherever you are, and notice that you are being held together. Right now, without any effort from you, the atoms in your chest are keeping their arrangement, holding the shape that is you, second after second. And they can do that only because the universe has a settled order, a strict speed limit that keeps cause ahead of effect and lets a pattern persist. Feel your hand resting on the blanket, the fingers keeping their form, and know that the force holding those fingers together is the identical force that would tear a starship apart at a fifth of the speed of light, doing its quiet, gentle work at the speed of a resting body instead. Feel the faint warmth in the room, tracing back through the wall and the window to a star that has burned steadily for 4.5 billion years, burning slowly and not exploding because energy in this universe is kept in strict and careful accounts, the same accounts that make a starship's fuel impossible. And feel, in the dark and the quiet around you, the enormous emptiness of space pressing in from every side, the same emptiness that strands us, the same emptiness that kept the stars far enough apart and the neighborhood calm enough that a world could hold still long enough to grow the very body you are lying in. 4 walls, 4 supports. Felt from the inside, at rest, they are not a prison. They are the reason there is an inside at all. Do you feel it now? Turn the cage over in your hands and look at it from the inside, and it stops being a cage. The 4 walls, felt from within, are the 4 supports of your own existence. The ceiling of light steadies the atoms of your body. The binding force that would wreck a ship at speed holds your hand together at rest. The conservation laws that tax a rocket keep your sun burning evenly. The empty distances that strand us keep the stars from crowding and let a world hold still long enough for life. The same 4 laws, read one way, are the reason we can never leave. Read the other way, they are the reason there is a we at all. And that turns the whole meaning of tonight, because it means the reason we can never escape the solar system is not some cruel accident laid over a friendly universe. It is the friendly universe, seen from the inside, telling us that the price of existing here is staying here. Part 13. The Strange Reason, Named. So let me finally answer the question the title asked, plainly, now that you have everything you need to feel the whole weight of the answer. What is the strange reason we can never escape the solar system? It is not the sun's gravity. We broke that grip almost 50 years ago, and a machine from the 1970s is drifting out of the sun's reach forever as you listen to this. It is not that our rockets are too weak, though they are, and it is not that we lack some clever invention, that is surely just around the corner. The strange reason is that there is no single reason. There is no one wall. There is a set of 4 separate physical laws, each of which, entirely on its own, we could survive, that happen to be wired together so that beating any one of them arms another. Say it slowly, because this is the whole thing. The distance is so vast that you must go fast to cross it in a lifetime. But going fast is capped by the speed of light, a ceiling built into space-time that no energy can breach. And even approaching that ceiling costs energy that grows with the square of your speed, a tax written into motion itself that no cleverness can lower. And the very speed you need to beat the distance turns the thin, harmless emptiness of space into a wall of radiation and micro-explosions and, somewhere along the way, one waiting pebble with the energy of a nuclear bomb. Go slow, and the distance kills you. Go fast, and the emptiness kills you. There is no speed that is both, because the 2 lethal zones overlap completely. That overlap, that welding together of 4 survivable limits into one unsurvivable shape, is the strange reason. The cage is not made of any single bar. It is made of the way the bars are joined. And the strangest part, the part I hope stays with you after the rest fades, is that the very same 4 laws that lock us in are the 4 laws that made us. The light-speed ceiling that traps us is what steadies the atoms of a body so a life can persist. The binding force that would shatter a starship is what holds a hand together. The energy law that taxes a rocket into impossibility is what lets a star burn slow and long enough for a planet to grow life. And the empty distances that strand us are what kept our corner of space quiet enough for that life to begin. The cage and the cradle are the same object. We can never leave, and we could ever exist, turn out to be 2 readings of a single sentence. That is not a tragedy. That is the deepest fact about our home. The universe did not build a prison and put us in it. The universe built the only kind of place where a thing like us could wake up, and that place, by its nature, has walls. Now, before we end, I owe you a piece of honesty, because I have spent an entire video telling you that we can never leave, and there is a long, embarrassing history of people saying never about exactly this kind of thing. Let me tell you my favorite example. In the year 1903, a respected newspaper published an editorial with the title "Flying Machines Which Do Not Fly," and it argued, with great confidence and a good deal of mathematics, that building a working flying machine might take humanity somewhere between 1 million and 10 million years. It was a serious argument by serious people, and the Wright brothers flew at Kitty Hawk 69 days later. 69 days, and 66 years after that first 12-second hop, human beings walked on the surface of the moon. There are few things that make a person look more foolish than confidently predicting the future of technology, and I am aware, saying never tonight, that I am standing exactly where that editorial stood. It is worth remembering just how fast that reversal happened, because it is easy to hear the dates and let them slide past. The editorial did not say flight was merely difficult, it said 1 million to 10 million years, a span longer than our entire species has existed, a span that reaches back before we were human at all. And the answer came in 69 days. Not 69 years, 69 days, less than the time between 2 full moons 3 times over. The people who wrote never were not fools. They were careful, educated, reasonable people, working from the best understanding they had. And they were wrong, not by a little, but by a factor of 10 million. And they were shown to be wrong before the ink had properly faded. That is the humbling thing about the word never when it is aimed at the future. It has a long history of being technically well argued and completely, spectacularly mistaken. And I want to hold that against everything I have told you tonight, honestly, without flinching, because the physics we have walked through is real, and the humility is also real, and a thinking person has to carry both at once. So let me be careful about what I am actually claiming. Everything we know says the four walls are real, and that they are coupled, and that no demonstrated physics repeals them. That much is solid. What I do not know, what nobody knows, is whether real means final. Maybe there is physics we have not found yet, a door we are as blind to as that newspaper was to powered flight. Maybe the thing that escapes is not us in our current form at all, but something we become, patient across centuries, or post-biological, or something we cannot yet picture. Or maybe, and this is the possibility I find most haunting, the whole framing is wrong, and the future of a species like ours was never out there among the stars to begin with, but somewhere else entirely, somewhere inward, somewhere we have not thought to look. We have assumed, without ever quite deciding to, that to have a future, a species must spread outward, must fill space, must plant itself around other stars the way our ancestors spread across the continents. But that assumption is a story we tell, not a law of physics. Perhaps a mature civilization does not spread outward at all. Perhaps it turns inward, into worlds of its own making, into depths of understanding or experience or simulation we cannot yet imagine, and finds there room enough that the locked door to the stars simply stops mattering. We do not know. It is only one more possibility among the ones we cannot yet see. But it is worth holding, because it loosens the grip of the sadness, the reminder that never leaving may not be the same as never growing. I genuinely do not know. Honest science, tonight, cannot tell you which. And notice one more time, because it is where we began, that there is no ceiling to break through. When we started tonight, I said that as reassurance. Point up, and nothing is holding you down. The way out is completely open, and it is. That part was always true, but you understand now the strange sting in it, the thing we could not see at the start. A ceiling would be something you could push against. A wall would have a location, a door, a far side. What actually holds us is the absence of any such thing, the open, endless distance itself, wired to the speed of light and the tax on energy and the fire in the emptiness. The very openness of the direction up is the trap. There is nothing to break through, and that is exactly the problem, because you cannot break through nothing. You can only cross it, and it is the crossing, not any barrier, that cannot be survived. But that not knowing is not a defeat. It is the most interesting thing in the sky, because it means that when you go outside tonight and point straight up into that open direction with no ceiling and no lid and nothing holding you down, you are pointing at a real and unanswered question, one that sits at the exact edge of what physics can say. The strange reason we can never escape the solar system is that the four laws which cage us are the same four laws which made us, and whether that cage is truly forever, or only looks that way from inside a young and clever species on its 68th day, is a thing no one alive can honestly promise you. So look up, and hold both of those at once, the wall and the wonder, the cage and the cradle, and rest easy tonight in the strange and beautiful fact that the universe which will not let you leave is the very same universe that against all the odds let you be here at all.